Welcome back to episode 12 of the Gray Files, where we peel back the layers of technology, economics, data science, and even the human condition itself, all in an effort to try and understand this vast and often perplexing world we live in. I'm your host, Erika Barker, and tonight we're continuing our journey in part 2 of our 3-part series, venturing into what data science really is. So in episode 11, I introduced you to the modern alchemists who have quietly become some of the most influential people in our society. Tonight, we're going where the real work happens, inside their mathematical laboratories, into the specific techniques that transform raw information into algorithmic power. We're going to understand not just what these tools do, but how they actually work, why they were invented, and what makes each one uniquely suited to different types of problems. To help us understand this hidden world, I'm going to introduce you to some fictional character data scientists whose experiences represent the real challenges and methods used by thousands of practitioners working in this field right now. Now, their stories may be fictional, but the mathematical techniques they're using are very real, and they are reshaping your world in ways you've never imagined. So brace yourself. This might be an episode you will need to listen to twice, maybe 3 times. We're covering a lot, so I'm going to be covering the mathematical methods being deployed right now to make decisions about your mortgage, your medical treatment, your job prospects, and what information appears in your feeds. Understanding them isn't optional if you want to navigate a world increasingly run by algorithms. Part 1. The Foundation. Linear Regression. Let me introduce you to Dr. Elena Simpson, a data scientist at a major real estate platform. Elena's current project seems straightforward. Predict house prices based on features like size, location, age, and condition. But what Elena is actually doing connects directly to a mathematical breakthrough that happened over 200 years ago. So let's venture back. In 1801, the Italian astronomer Giuseppe Piazzi discovered what he thought was a new planet, but later was classified as the asteroid Ceres. So he tracked it for 41 days before it disappeared behind the sun. The question became, where would Ceres reappear? Multiple astronomers had made observations, but their measurements were inconsistent due to the instrumental errors and atmospheric interference. Carl Gauss, then just 24 years old, solved this problem by inventing what we now call the method of least squares. Gauss realized that instead of picking one best observation, he could find the line that minimized the total error across all observations. When Ceres reappeared exactly where Gauss predicted, it established his reputation and gave birth to modern regression analysis. So, I know that was a lot, but we're going to dive into this further. Here's how linear regression actually works, and why it's still the foundation of almost everything in data science. So Elena's algorithm examines thousands of house sales and asks a deceptively simple question. What's the mathematical relationship between house features and price? Think of it like this. The algorithm is trying to build a formula, like a recipe. it might discover that the recipe for a house prices is start with a base price of $200,000. Then add $127 for every square foot, plus $15,000 if there's a garage, plus $23,000 if it's near good schools. The algorithm's job is finding those exact numbers. The $127 per square foot, the $15,000 for a garage, by testing millions of possible combinations until it finds the formula that makes the most accurate predictions across all the houses it's studied. Now, here's the clever part that Gauss figured out over 200 years ago. When the algorithm makes a mistake, say it predicts a house will cost $300,000, but it actually sells for $320,000, it squares that error. Let me explain. So a $20,000 mistake becomes $400 million when you square it. Why do this? Because it forces the algorithm to really care about big mistakes while not getting too distracted by tiny errors. So when Elena's model encounters a new house, 3,200 square feet, built in 1995, 2-car garage, excellent schools, it plugs these values into the equation and generates a prediction. But linear regression doesn't just give you a number. It also provides confidence intervals that tell you how certain the prediction is. Okay, that's a lot to understand over a podcast without visual cues. So let's do this instead. So imagine you have a chart where each dot represents how much someone studied. And this is going to be on our x-axis. That's the line that goes from left to right. And then what score they got on a test, and that's going to be on the y-axis. That's the one that goes up and down. Some people studied a little and got low scores. Others studied a lot and got high scores. But the dots aren't in a perfect line. They are scattered all over our chart. So linear regression helps us draw the best straight line through those dots to show the general pattern. So more studying usually means a better score. That line is called the regression line. It doesn't go through every dot, obviously, but it tries to get as close as possible to all of them. It does this by minimizing how far off each dot is from the line. Those are called errors or residuals. The goal is to make those errors as small as possible overall, and we usually measure that using something called least squares. Once you have the line, you can predict things. For example, if someone studies 5 hours, you can look at the line to guess what their score might be, even if you don't have that exact dot. That's why linear regression is powerful. It shows trends and helps you make smart guesses based on patterns and data. It's like connecting the dots, but in the smartest, most balanced way. So the mathematics here reveals something profound about the nature of prediction itself. Linear regression works best when relationships are actually linear, when variables have roughly normal distributions, and when errors are randomly distributed. When these assumptions break down, which they often do in the real world and in real world data, you need more sophisticated tools. Part 2. When straight lines aren't enough. Logistic regression. This brings us to Dr. Marcus Chen, working on medical risk assessment at a major hospital system. Marcus faces a fundamentally different challenge than Elena. He's not predicting continuous numbers like house prices, but binary outcomes like whether a patient will survive surgery or experience complications. Linear regression works great when you're predicting numbers, like how many points someone might score, but it falls apart when the answer is a yes or no question. Like, will this person survive surgery? It might tell you there's a 150% chance they will, or a negative 30% chance they won't. Neither of which makes any sense, because probabilities should always be between 0% and 100%. In the 1940s, scientists working on medical problems came up with a smarter method called logistic regression. So instead of trying to guess the probability directly, which can severely go off the rails, they first transformed the question using something called log odds. And that's a fancy way to represent how likely something is, but on a scale that doesn't blow up. Once they had that, they used a special math function to turn those log odds into a clean, normal-looking probability. That special math function is called the logistic function, and it draws a smooth S-shaped curve. And this curve always gives you an answer between 0 and 1, so you'll never get a ridiculous 150% chance again. It gently pushes extreme guesses back into the real world, which is why it's so useful for things like predicting if someone will click a link, or pass a test, or survive a disease. It's smart math for yes or no answers. So here's how Marcus uses logistic regression to assess surgical risk. The algorithm examines patient age, medical history, current health metrics, type of surgery, and dozens of other factors. Instead of generating a linear combination of these features, it feeds that combination through the logistic function, which smoothly maps any real number to a probability between 0% and 100%. The mathematics works like this. The algorithm still creates a formula just like linear regression, but instead of using that formula's answer as the final prediction, it puts that answer through something called the logistic function. So think of it as a mathematical translator that converts any number into a probability between 0 and 100%. So if the formula spits out a really high number, the logistic function translates that to something close to 100% probability. If the formula gives a really low number, it becomes close to 0% probability. Marcus's system might determine that a 45-year-old marathon runner has a 2.3% complication risk for a specific procedure, while an 80-year-old diabetic faces a 34.7% risk for the same surgery. The algorithm learned these relationships by examining thousands of historical cases, gradually adjusting its coefficients to maximize the likelihood of correctly predicting actual outcomes. So we learned that logistic regression is smarter than linear regression for yes or no questions, but it still makes a big assumption. It thinks the relationship between your inputs, like age, blood pressure, or medication, and the outcome, like getting better or not, follows a nice, smooth formula. And that's fine when things are simple, but real life isn't always that neat. Let's say Marcus is studying patients and notices that a certain medicine only works well for older people, but makes younger people worse. Or maybe a lab test score only matters when it's really high or really low, but not in the middle. These are nonlinear or interaction effects, basically patterns that don't follow a straight line or simple curve. Logistic regression can't handle those very well because it's stuck trying to fit everything into a fixed shape. To deal with these messier patterns, Marcus needs more flexible tools, algorithms that don't assume what the pattern looks like ahead of time. These tools can discover complex hidden relationships in the data without being told what shape to look for. It's like upgrading from using a ruler to using a 3D scanner. You're no longer guessing the shape, you're finding it. Part 3. Divide and Conquer. Decision Trees. Enter Dr. Elisa Rodriguez, working on fraud detection at a major credit card company. Lisa faces a problem that defeats both linear and logistic regression. Fraudulent transactions don't follow neat mathematical relationships. They're designed to mimic legitimate purchases while hiding their true nature through constantly evolving tactics. Decision trees approach this challenge through a completely different strategy. So instead of finding mathematical equations, they play an elaborate game of 20 questions, systematically dividing the data into increasingly pure groups. The algorithm starts by examining all possible questions it could ask about a transaction and picks the one that best separates fraudulent from legitimate cases. Maybe it discovers that transactions over $500 are suspicious. But not all large transactions are fraudulent, and not all fraud involves large amounts. So the algorithm splits the data. Transactions over $500 go to one branch. Transactions under $500 go to another. Then it asks another question for each branch. For large transactions, maybe the next best question is, was this at a gas station? For small transactions, maybe it's, is this the customer's first purchase at this merchant? But how does the tree know which question to ask first? Well, it uses math to figure out which question makes the biggest difference. It picks the one that splits the data in a way that reduces confusion the most. That's called information gain or Guinea impurity. Both are ways to measure how much each question helps the tree get closer to a clean, confident answer. Now here's what makes decision trees powerful. They automatically discover combinations that would be impossible to think of in advance. The algorithm might learn something like $50 purchase at grocery stores? Almost always legitimate. But $50 purchases at electronics stores late at night from customers who never shop electronics? Highly suspicious. The final tree looks like a flowchart and reads like a detective's reasoning. If the transaction is over $500 and it's at an electronics store and it's after 11 p.m. and the customer has never bought electronics before, then there's an 87% chance this is fraud. But decision trees have a dangerous flaw that data scientists call overfitting. They can become too specific, memorizing weird coincidences instead of learning real patterns. A tree might create a rule like if the customer's name starts with J and the amount is exactly $47.32 and it's at Joe's Pizza, then it's fraud, which is completely useless for catching actual criminals. This overfitting problem led to one of the most important insights in machine learning. Sometimes you need multiple perspectives to get the right answer. Part 4. The Wisdom of Crowds. Random Forest. Dr. James Park, working at a financial services company, discovered that individual decision trees, while interpretable, can be unreliable and overly specific to their training data. His solution draws inspiration from an unexpected source: democracy. Instead of relying on one decision tree, James creates hundreds of them, each trained on slightly different subsets of the data, each asking slightly different questions. Then he lets them vote on new cases. This technique is called a random forest, and it represents one of the most powerful ideas in modern machine learning: ensemble methods. Here's the clever part. James deliberately makes each tree in his forest different. Some trees see only customer income and spending patterns. Others focus on payment history and credit utilization. Still others examine demographic information and account behavior. Each tree becomes an expert in different aspects of the prediction problem. The mathematics of why this works relate to the bias-variance trade-off, one of the fundamental principles of machine learning. Individual trees can be highly accurate on their training data, but unreliable on new cases, something we call high variance. By averaging predictions across many diverse trees, the forest reduces this variance while maintaining the ability to capture complex patterns. When a new loan application arrives, all trees vote. Tree number 47 might predict approve. Tree number 203 says deny. Tree 156 says approve. James counts the votes and goes with the majority decision. Individual trees might make mistakes, but the collective wisdom of the forest is remarkably robust. The mathematical foundation rests on the law of large numbers. As you average more independent estimates, your combined prediction becomes more reliable, as long as individual predictors are better than random chance. Random forests work because they create many diverse, reasonably accurate predictors and combine them intelligently. But even random forests have limitations. They work well when you have clear features and labeled examples, but they struggle with high-dimensional data like images, text, or complex sequential patterns. For those challenges, James is going to need algorithms that can automatically discover relevant features rather than relying on human feature engineering. Part 5. Finding Boundaries in Chaos. Support vector machines. Things are going to get a little complicated in this part. So let's start with something familiar: dimensions. So in grade school, you probably learned about the x-axis and y-axis. You plot things left to right and up and down. That's two-dimensional space and what our linear and logistical regression models work on. Add a third axis, called the z-axis, to go along with the x-axis, left to right, and y-axis, up and down, and you're now working in three-dimensional space. Now, in this space, you're not limited to just plotting flat points on paper. You can represent depth, which is how objects appear closer or farther away. Each point is defined by three values: x, y, and z. And you can use these axes to plot not only position, but also things like motion, rotation, velocity, or even force vectors. In computer graphics, this is exactly how 3D worlds are built. Every object is made of thousands of tiny points called vertices, each with an x, y, z coordinate. These points are connected into surfaces lit by virtual light sources, and then transformed using matrices to simulate movement and perspective. Your GPU, or graphics processing unit inside of your computer, projects this 3D world back into a 2D image, or what you see on your screen, while maintaining the illusion of depth and realism. And that's the foundation of everything from Fortnite to Pixar films. Now, back to data science. Every time you add a new piece of information, like how much someone spends, what time they shop, how they respond to coupons, you're adding another dimension. Sarah Kim, a data scientist working on customer segmentation for a major retailer, deals with this kind of high-dimensional space all the time. Her data might live in 80 dimensions, or maybe 90 dimensions, or 100, each one representing a unique behavioral trait. Now, to make sense of this complexity, Sarah uses support vector machines, or SVMs for short. Think of a table with red and blue marbles scattered across it. Each marble represents a customer, and your job is to draw a line that cleanly separates the two colors. In 2 dimensions, that's pretty simple. In higher dimensions, you draw a hyperplane, which is a multi-dimensional wall that separates customer types. The SVM doesn't try to perfectly fit every marble. Instead, it focuses only on the support vectors. Those are the marbles closest to the dividing line, the ones hardest to classify. That focus makes the model both powerful and resilient. It ignores the noise and builds a boundary that generalizes well to new data. But here's the problem. Sometimes the marbles are arranged in a way that no straight line or hyperplane can separate them. So imagine red marbles in a circle surrounded by blue marbles. In 2 dimensions, you're stuck. But if you could lift the whole arrangement into a 3rd dimension, bend the plane into a bowl, for instance, you could suddenly draw a flat sheet that slices through and separates them perfectly. This is where kernels come in. So a kernel, and that's spelled Kernel, not like how you spell a military rank, is a mathematical function that lets the SVM pretend it's lifting the data into a higher dimensional space without actually doing all the heavy lifting. It calculates how similar or different 2 data points are as if they were in that larger space. It's like tricking the algorithm into seeing curves as straight lines. This saves massive amounts of computation while still unlocking complex patterns that were hidden in lower dimensions. Sarah uses a specific kernel here called a radial basis function, or RBF kernel. It's actually one of the most popular and flexible types. Now, the RBF kernel measures how close 2 points are to each other in that higher dimensional space, but it does it in a smooth, nonlinear way. Instead of drawing sharp boundaries, it creates a smooth influence around each support vector, like a gravitational field. Closer points have stronger effects. The farther away a data point is, the less it influences the boundary. This means the RBF kernel is especially good when there's no obvious linear pattern, like when some customers buy frequently during sales and others spend big only on full-priced items. You don't need to tell the algorithm what patterns to look for. The RBF kernel helps the SVM discover those patterns automatically, even when they twist and bend in dozens of unpredictable directions. Now, although the RBF kernel behaves like it's working in infinite dimensions, it never actually computes them. It skips the mess and jumps straight to the answer. And that's what makes kernelized SVMs so powerful. They scale the complexity of real-world data without scaling the computational cost. Now, I know that section was a lot, and we're going to dive into this a little bit more heavier into its own respective podcast in the future. But I hope this gives you a better understanding on how SVMs and kernels work. Part 6, Learning Without Teachers, Clustering Algorithms. Not every problem in data science is about prediction. Sure, sometimes we want to know if a customer will click a button or if a patient will survive a procedure, but other times the real value comes from asking a different kind of question, one that's more open-ended, more exploratory. What patterns are hiding in this data, even the ones I don't know to look for? And that's exactly the kind of problem Rachel Martinez works on at a major streaming service. She isn't looking for cause and effect. She's not trying to predict who will cancel their subscription or what show will trend next week. Instead, she's asking, what kinds of viewers do we actually have? She's using a technique called clustering to let the data organize itself to discover natural groupings without anyone forcing labels onto them ahead of time. One of the classic tools for this is called k-means clustering. It's simple in concept, but surprisingly powerful. Picture all your viewers as dots on a giant invisible graph. Each dot's position is determined by their behavior, how often they watch, what time of the day they tune in, how long they stick with a show, how much they binge, what genres they like. These aren't plotted in just 2 or 3 dimensions. This could be 10, 50, or even 100-dimensional space. Now, imagine dropping a handful of random centers into that space, which are starting guesses for where your groups might be. The algorithm then plays a game of musical chairs. Every viewer gets assigned to their closest center. Then each center moves to the average position of the people assigned to it. Then everyone switches chairs again. This repeats over and over until the centers stop moving. When that happens, the groups have stabilized. Each viewer now belongs to a cluster of others who behave similarly. This might uncover segments like binge watchers who finish seasons in a single weekend, casuals who stretch episodes out over weeks, genre specialists who stick to horror or documentaries, samplers who hop across genres but rarely finish a show, and late-night repeaters who rewatch familiar content during insomnia hours. Now, no one told the algorithm to look for these patterns. It discovered them. That's the power of unsupervised learning. You don't need a label, a score, or a yes-no outcome. You just need behavior. But k-means has a blind spot. It assumes all clusters are roughly the same size and shape. Imagine trying to draw perfect circles around every neighborhood in a city. That might work in the suburbs, but not in a city full of winding roads and oddly shaped blocks. What if one group is tiny and tightly clustered while another is huge and spread out? What if some people don't fit any cluster at all? That's when Rachel uses something more flexible, like DBSCAN, short for Density-Based Spatial Clustering of Applications with Noise. Wow, that's a lot. So, to explain this, instead of looking for neat circles, DBSCAN looks for clumps, dense regions of data points. If the points are packed close enough together, DBSCAN calls that a cluster. If a point is too far from everything else, it gets flagged as an outlier. It doesn't matter what shape the cluster is, snake-like, crescent-shaped, blob-like, it just needs to be dense enough. Think of it like this. K-means is trying to build neighborhoods on a map with perfect little fences. DBSCAN is looking at where people actually live, finding communities wherever they naturally form, even if the boundaries are messy and irregular. And it's smart enough to say, hey, this person's behavior is so weird. They don't belong to any of these clusters. That's useful. Outliers matter. At the core of all clustering is one simple assumption. Things that are similar should be grouped together. But how do you define similar? The most common way is to use Euclidean distance, the straight line distance between 2 points in space. If two customers have very close behaviors, they'll be close together in that space. But in high-dimensional data, straight lines aren't always the best measure. That's where we switch to other metrics, like cosine similarity, which measures the angle between 2 points instead of the raw distance. That's especially useful when the magnitude of the numbers doesn't matter, only the pattern or direction. And here's the real-world twist. Sometimes what makes customers similar isn't obvious mathematically. Maybe horror fans behave differently based on whether they binge or snack watch. Maybe parents have a unique rhythm based on school schedules. Now, if you know things like that, which is domain knowledge, you can bake it into the similarity metric. You can even create custom distance functions that weigh some behaviors more heavily than others. So while clustering doesn't give you a prediction or a label, it gives you something just as powerful. A map of the data's natural structure. It tells you not just what's happening, but how behavior organizes itself. It shows you patterns that were there all along, hidden in plain sight, waiting to be revealed. Part 7. Dimensionality Reduction. Finding Hidden Structure. Rachel now has another problem. She is swimming in data. She's working with a massive viewer data set from a streaming service. But she's not just looking at one or two things like hours watched or favorite genre. Her data set includes hundreds of variables. How long someone watches, which genre they prefer, which days they watch the most, whether they use a phone or TV, how often they skip intros, what they search for, if they even listen to recommendations. Now, Imagine trying to group people based on all of that at once. It's like trying to read hundreds of books at the same time. Everything becomes noise. Nothing stands out. And that's the problem. Too many features. And it's one of the most common headaches in data science today. To cut through that mess, Rachel turns to something called Principal Component Analysis, or PCA. It's a tool that helps simplify data without destroying its meaning. Think of PCA like a super smart compression tool. It looks across all the variables and says, what's actually driving the differences in behavior here? What are the strongest patterns hiding underneath all this detail? Here's what it does. PCA creates new features called principal components that capture the essence of the data. They're built from the original features, but they summarize what matters most, kind of like cliff notes from your favorite novel. The first principal component, that's the direction where the data varies the most. It's the biggest pattern. The second component captures the next biggest pattern, but in a completely different direction. Each new component adds a little more information, but with diminishing returns. So in Rachel's case, PCA might find one component that reflects total engagement, like how much someone watches overall. Another that captures genre diversity. Do they stick to one type of show or explore many? A third that maps to time of day habits, late night bingers versus weekend warriors. These components are powerful because they're combinations of many little signals. They're like chords built from individual notes. You don't need to hear every note to understand the song. By using PCA, Rachel can take her 100+ features and shrink them down to, say, 5 or 10 powerful ones, and still explain most of the important variation in viewer behavior. That's called dimensionality reduction, cutting down the number of variables without cutting out the insight. And it matters, because when Rachel feeds these new components into a clustering algorithm or a visualization tool, everything works better. It's cleaner, faster, and way more accurate. But there's a catch. PCA is a linear method. It assumes the world follows straight lines, simple relationships. And as we all know, human behavior isn't always that clean. So when the patterns are more tangled, when the relationships are nonlinear or curvy or just really weird, Rachel uses something more advanced. t-SNE or t-SNE, which is short for T-distributed stochastic neighbor embedding. Yeah, it's a mouthful. Trust me, I know. But here's the idea. Instead of trying to explain the whole data set globally, t-SNE zooms in on local neighborhoods and makes sure that people who behaved similarly in the original data stay close together when the data is compressed. It doesn't try to explain everything. It focuses on preserving the local structure, the little clusters, the tight groups. It's less like a map and more like a microscope. With t-SNE, Rachel might discover unexpected clusters, groups of users who behave almost identically, even though they look different at first glance. But t-SNE has trade-offs. It's harder to interpret. It doesn't scale well to very large data sets, and it can sometimes create patterns that look meaningful, but really aren't. Still, for exploration, it's one of the best tools out there. Underneath both PCA and t-SNE is a deep but beautiful idea. Just because your data has hundreds of variables doesn't mean it needs them. The real structure, the real behavior, often lives on a lower dimensional surface inside of all that noise, like a folded up sheet of paper hiding in a ball of yarn. Dimensionality reduction is how you unfold it. You flatten the complexity, you reveal the patterns, and suddenly, instead of noise, you've got a story you can actually tell. And that is when data science becomes not just smart, but powerful. Part 8. The Neural Revolution. Deep Learning. The earlier techniques we've talked about, things like clustering, PCA, support vector machines, well, they were actually all created decades ago. Back then, computers were slow and storage was pretty expensive. These methods were designed to be efficient and simple. But over the past 20 years, the field has shifted. We've gained access to more data, more powerful computers, and a new class of algorithms called neural networks, which make deep learning possible. Michael Peters works at a company building autonomous vehicles. His systems have to detect pedestrians, read traffic signs, and understand road conditions while the car is moving and without making mistakes. Standard machine learning algorithms can't handle that level of complexity. Neural networks can. A neural network is a system made up of simple units called artificial neurons. Each one takes in some inputs, multiplies them by internal weights, adds the values together, and runs that result through a math function that transforms the number in a useful way. That output is then passed to the next layer of neurons, and the process repeats. What makes this powerful is how these layers are stacked. The first few layers might detect simple patterns like edges or color, contrast in the image, and the next layers combine those into more meaningful features like textures or shapes. Deeper layers can recognize objects like a stop sign, a pedestrian, or another car. This process of refining the data step by step is what gives deep learning its name. Each layer transforms the data just a little, and the network gradually builds a more complete understanding of what it's looking at. The network improves through a process called training. It makes a prediction, checks how far off it was, and adjusts the internal weights slightly to do better the next time. This is done using a method called backpropagation, which calculates how much each part of the system contributed to the error. Over thousands or millions of examples, the network gets better at its task. Now, modern deep learning systems can have hundreds of layers and billions of adjustable weights. Training them takes a lot of data and computing power, but once trained, they can handle complex, real-world tasks with high accuracy. One of the key differences between deep learning and older methods is that deep learning systems don't need a human to define the important features ahead of time. Instead of saying, "Look for wheels and eyes and vertical lines," the network figures out what matters based on the data it sees. This is called representation learning. Different parts of the network work better with different kinds of activation functions. For example, ReLU or ReLU only passes positive values and works well in deep networks. Sigmoid compresses values into a range between 0 and 1, which is useful for binary outputs. TANH, spelled T-A-N-H, centers the data around 0, which can help balance things during training. Now, different types of neural networks are used for different kinds of data. Convolutional neural networks, or CNNs, are built for image recognition. They focus on how nearby pixels relate to each other. Recurrent neural networks, or RNNs, are used for things like speech or text, where the order of the input matters. They can remember past inputs when making new predictions. Deep learning is now used in voice assistants, facial recognition, medical image analysis, and yes, autonomous vehicles. What sets it apart is that it scales. When there's more data and more computing power available, it doesn't just keep up, it gets better. These systems work because they're structured, trained, and optimized for complex pattern recognition. That's why they've become the foundation for modern AI. Part 9. The mathematical arsenal deployed. You know, what's really remarkable about modern data science is how these techniques work together in production systems. Elena might start with linear regression to understand basic price relationships, then use decision trees to capture complex interactions, then ensemble multiple models with random forests to improve accuracy, then apply neural networks to process satellite imagery for neighborhood assessment. Marcus combines logistic regression for basic risk assessment with clustering algorithms to identify patient subgroups, then uses support vector machines to detect unusual cases that might need special attention. His ensemble approach leverages the strengths of each technique while compensating for individual weaknesses. Lisa's fraud detection system runs multiple algorithms simultaneously, clustering to identify normal spending patterns for each customer, neural networks to process transaction sequences and detect temporal anomalies, and gradient boosting machines to make final classification decisions based on hundreds of engineered features. The art of data science lies in understanding when to use which tool. Linear regression when relationships are simple and interpretability matters. Decision trees when you need transparent logic and have categorical features. Random forest when you want robust performance without much tuning. Support vector machines when you have high-dimensional data and clear class boundaries. Neural networks when you have massive datasets and complex patterns that defy traditional feature engineering. Each technique makes different assumptions about data structure and optimization objectives. The mathematics reveal these assumptions explicitly. Linear models assume additive relationships. Tree-based methods assume recursive partitioning works well. SVMs assume margin maximization improves generalization. Neural networks assume hierarchical representations are useful. It's practical necessity to understand these mathematical functions and foundations. When the model fails in production, when predictions become biased, when performance degrades over time, the solution lies in understanding why the mathematics don't match the reality of your specific problem. So the techniques we've explored tonight form the core arsenal of modern data science. But they're not just abstract mathematical tools. They are the specific algorithms making decisions about your life right now. Every loan application, every job recommendation, every medical diagnosis assistance, every content suggestion involves these exact mathematical approaches. The power of these methods isn't just in their individual capabilities, but in how data scientists combine them, adapt them, and deploy them to solve real-world problems. Understanding how they work, how they really work at the mathematical level, is the first step to understanding how algorithmic power operates in our society. Next time on the Gray Files, we'll investigate how these mathematical tools are reshaping power structures, creating new forms of inequality, and raising questions that even the practitioners themselves struggle to answer. But you'll approach those discussions with something most people lack, and that you now somewhat understand: an actual understanding of what's happening under the algorithmic hood.